I was looking for the videos and the notes for section 4.2, couldn't find them, so we're going to repeat those, because you may be right, I don't think we did cover it. I think I went through them really quick, but never really covered it. So that's what we'll cover today. The last two sections of chapter 4, I want to reserve one whole day for it, because section 6 deals with word problems. Related, what's called in mathematics, related rate problems. We're going to look at, for example, a box question. How big should the piece of material be if you want to build a box that's 12 inches by 2 inches? 12 inches square by 2 inches high. So how big should the material be for you to make an entire box of this? That kind of stuff. So we're looking for those kind of related rate problems. And the last section, section 7, deals with something that's called an iterative technique. It's called the Newton's method. It's where you start off with an initial guess, and you keep on going through the cycle over and over and over until you get to an answer that keeps on repeating itself. It's called an iterative process, and those take a long time. So I want to save that for our class on Wednesday, and that'll finish up chapter 4, and then next week we do chapter 5 to see how far we get. Also have to look at the tests, because apparently the tests are not testing calculus, they're testing algebra. So I may have put the wrong test in there. So don't do your test for the rest of the course until I fix those. So yeah, I want you to test on calculus, not algebra.
Yes, is it the one with the quiz or the actual?
The actual test.
Okay, then I haven't done it.
Yeah, so don't do it, please. You know, next week's the last week of classes. This is the last week of April. Then we start 1 week of May, then we have finals. It'll be online. Yeah, my final is online, so if we want to, we take that last day where we're supposed to have a final and have a review class, or you just take the test. In this section, we deal with two major theorems. One of them is called Rolle's theorem, and the other one is the main one, is the mean value theorem. Basically what these are, they're comparing two functions that have the same derivative. So that's what the objective is on this section. Let's define Rolle's theorem. Suppose you have a function y equals f of x. It is continuous over a closed interval a, b, and it's differentiable at every point inside the open interval AB. Call those interior points. But here it is. If f of A equals f of B, there exists at least one point at C, which is inside the open interval AB, it's an interior point, such that, oops, that f prime at C equals 0. What does that mean? When it's f prime equals 0, what does that mean? Well, yeah, it comes from a constant, yes, but we're looking for f prime at C equals 0. Vertex. It's the maximum minima point. Remember, the first derivative is slope. Slope equals 0 at x equals C. That's what it's telling us. Which is the maximum, it's a vertex. So, a maximum or minimum only occur at interior points. What are interior points? Well, inside the open interval AB, right? It's any points inside that open interval AB, which is at FA, FB, right? Where the following three conditions apply. F prime of x is equal to 0. F prime of x is undefined, or f of a or f of b is undefined. Not possible to get to. We know this one. F prime of x equals 0. We just talked about that. Why is f prime being undefined able to be a maximum or minimum? What is that example of? If f prime is undefined. What kind of graph gives you an undefined slope? From algebra, what's an undefined slope? It is a straight line, but no, it only have two options, either horizontal or vertical. Which one is it? Which one's undefined? Vertical line. So, when functions approach a vertical slope, then it's undefined. So it happens there. So, if f of x has a derivative, f prime of x, at every point in the open interval AB, then the function derivative cannot be undefined. So if a function is continuous and it has a derivative at every point inside the open interval, then this one cannot exist. Why? Let's look at the Atari function. It has an asymptote at x equals 0. If A and B, if our open interval was A and B here, on both sides of the x equals 0, is the function continuous? No, because there's an asymptote. Okay, so that doesn't work. So how about if A was moved to that side? Is the function continuous inside this open interval? Yeah, it's continuous because every point inside there exists. If every point exists, then it's differentiable. That means the first derivative means the slope exists at each one of those points. So if each one of those points has a derivative, then number 2 cannot be true. So that's what we're saying is number 2 exists only when you have an asymptotic function, a value asymptote. Note, if the function f is not differentiable, at any point in the open interval AB, then Rolle's theorem doesn't work. So here are some examples of where it wouldn't work. Discontinuous at one of the endpoints. Discontinuous has a jump discontinuity at an interior point. Or has a location where it's continuous but not differentiable. Remember, in chapter 2 we said if you have a point, it's not differentiable because the limit doesn't exist at that point. These are 3 conditions where it doesn't work. Here's an example. F of x equals x cubed plus 3x plus 1. So show that there is only one real solution. Remember the intermediate value theorem. What does that mean? What was the intermediate value theorem? Exactly. Very good. Intermediate value theorem says function is on an open or closed interval. If f of a is positive and f of b is negative, then there exists at least one point at C where f of x or f of c equals 0. So if you can find two values, a function where it gives us different signs, one of them is positive, one of them is negative, in order for that to happen, there has to be at least one point where it crosses the x-axis, has a solution. So can we do it with this? With this function? I like to use negative 1 and 1. Negative 1 cubed plus 3, negative 1 plus 1. Positive 1 cubed plus 3 times 1 plus 1. So go ahead and work that out. What's the first one going to give us? The second? So we see that you have opposite signs. So at least one solution exists. How would we check for more than one solution? Derivative finds us the slope of the curve. That finds us a vertex. So we can use Rolle's theorem. Remember, Rolle's theorem. It's continuous, it's differentiable. So if f of a equals f of b, then there exists at least one point at c inside the interval such that f prime of c equals 0. Can we find a place where f of a equals f of b? And then, can we find a place where it equals 0? So let's look at the function. What's the derivative going to give us? (3x squared plus 3). Set that equal to 0. Solve for x. What do we get? Subtract 3 from both sides. Divide by 3. Subtract 3. Divide by 3. What's going to happen here? X squared equals -1. It's going to be imaginary. So there's no place in that interval where the first derivative equals 0. Which means there can't be more than one solution. If it was more solution, then we'd have, think of it this way. If this derivative existed, no, at -1, 1, we have opposite signs. So they're on opposite sides. If the derivative existed, then there'd be another place where the curve goes back down. Which means at that point, there could be an interval where the x-intercept happens more than once. But since this never happens, the graph has to be a continuous increasing function. So there are no other solutions. So only one solution in this equation. Everybody follow that? We use Rolle's theorem because Rolle's theorem tells us if you use intermediate value theorem, you have at 2 points you have different signed functions. Then you know it crosses the x-axis at least once. What determines if it crosses more than once is if we find the first derivative, and if you can make it equal 0, that means it bends, and it either bends up or bends down. That means you can have more than one solution. Because you can have as many solutions as you have derivatives to equal 0. Right? So if that one doesn't work, we can't do it. So that's Rolle's theorem. Now, the mean value theorem. Suppose you have a function y equals f of x. That is continuous over the closed interval AB and differentiable at every point in the closed interval AB. And there exists at least one point at C inside the closed interval AB such that f of B minus f of A over B minus A equals f prime at C. What does that mean? Then there is a tangent line to the curve that is parallel to the secant line to the endpoints A, B. So it would be A, f of A, and B, f of B. The word mean value. What does the word mean mean? What's another name for the word mean? Average. So that's what this is. This is the average. It's also, if you look at it, it also defines the slope. It's an instantaneous average at a given point. That's why it says here that the tangent line to the curve is parallel to the secant line. What does that look like? Here we have A and B. There's the secant line. Then there's also a tangent line that has the same slope at some point C inside the open interval AB. This is the tangent. This is the secant. What do you notice about this? C has to be an interior point of the interval AB, which is what we've been looking at all along with the Rolle's theorem, intermediate value theorem. There has to be a value between inside the closed interval between A and C, A and B. Look at the definition of the mean value theorem again. Suppose that we have a function f of x, it's continuous on a closed interval, and differentiable at every point on the open interval. On the open interval AB. This part is very important. What happens at the endpoints, or does it matter? It's an open interval, so you can't get to the endpoints. So what this thing says, it's differentiable at every point in the open interval. So you have to have an interior point. So notice the derivatives at the endpoints do not have to exist for this to be true. So for the mean value theorem, the derivatives at the endpoints do not have to exist. Let's look at an example. F of x equals x squared. is continuous on the closed interval 0, 2. And differentiable on the open interval 0, 2. Use the mean value theorem. And let's find me the C value. So the first thing you got to do. What's the first thing you have to check? Endpoints. So we have to find f of 0 and f of 2. F of 0, what's the value? F of 2? Step 2, using the mean value theorem, we get. So how would you use the mean value theorem here? Remember, it's f of b minus f of a over b minus a equals f prime at c. We know f of b? It's 4, because this is f of a, this is f of b. So we have 4 minus 0, and this is a, and this is b. We have 2 minus 0. Four divided by 2 is 2. It's not the answer, it's what we're looking for. What this says is there has to be a derivative, some point where the first derivative equals 2. There has to be in order for the mean value to work, that means we have to be able to find a value c of the first derivative that it equals 2. So what's the first derivative? X. So f prime at some value c has to equal 2. So 2x equals 2. X equals 1. So what does that tell us? Look at the definition of mean value theorem. What does it tell us? Tells us mean value theorem tells us that the average rate of change is equal to the instantaneous rate of change at some value C. Here's another example, using one with physics. If a car accelerating from 0 takes 10 seconds to get to, say, 500 feet. That's to get to say go. To go 500 feet. Then its average velocity is the mean value theorem says that at some point along the way, the acceleration must be exactly what? How would you use the mean value theorem here? What's the average velocity? On the mean value theorem, what's the average part of the mean value theorem? Right. That's the average. Now, from this information, what can we plug in there? What are our A and B? What's A? 0. What's B? Why? Why is it 0 and 10? Why not 500?
That's how long it takes.
Yes. In physics, time is always the independent variable. Time is always the x-axis. In this case, acceleration, velocity, speed, distance, those are always the y, the dependent variables. Because if something is tossed, the distance of it depends on how long the thing's in the air. So that's why 0 and 10 are our independent variables. So that's A and that's B. So what's f of B? What's f of A? F of B is where it finishes. F of A is where it starts. So we have 500 divided by 10 is 50 feet per second. So the mean value theorem says that at some point along the way, the acceleration must be exactly 50 feet per second. Because this thing is the first derivative of the distance, of the velocity. What are corollaries? Corollaries to what? Corollaries to the theorem we're talking about, the mean value theorem. So there are two other instances that exist. The first one, corollary 1. If the first derivative is 0 at each point in the open interval, each point x in the open interval, so we say that x is contained in AB at every point. Then f of x equals c for every x in the open interval. Let's look at this as. If f prime of x equals 0 at every point in the open interval, then f of x has to equal c. What is that telling us? Because the mean value theorem says that there could be one or more values c in the open interval where the first derivative equals the average. But this one says every point in the open interval AB, every point is equal to 0. So you said this earlier today. What does this mean? Yeah. In other words, if the first derivative is 0 at every point, that means the only way that could be true is if the function's a constant. Because let's look at this. Here's an example. If f of x equals 5, what's the slope of that graph? slope is 0 because it's a horizontal line. Going through y equals 5. Since the slope is equal to 0, that means no matter what x you give me, x1, x2, x3, the slope of this curve at those points is always going to be 0. And that's what the first corollary says. Second corollary. Corollary 2. If f prime of x is equal to the same thing as g prime of x, or every x in the open interval AB, then there exists a constant c such that f of x equals g of x plus c. For every x in the interval. So what this thing really says is this. F of x equals g of x plus c. If they were equal, I mean, these are examples of like parallel lines. They have the same slopes, but they have 1 point different from each other. If we move g of x over, if we subtract g of x from both sides, then what we have is f of x minus g of x equals some constant. For the x in the AB. Which also says that f and g are differentiable if h equals f minus g, some function h of x equals f of x minus g of x, and h prime of x equals f prime of x minus g prime of x is equal to 0. And the only way this could be true if and only if h is equal to some constant. This is the corollary. It's one of those, duh, yes, it's no sense, no doubt. Because think of this. H equals f of x. F of x was g of x plus c. That's what f of x was. So we have g of x plus c minus g of x. So the h has to equal c. Algebraic, it tells us that. But here we're proving it with the derivatives. So get number 4. Example 4. Find an f of x whose first derivative is sine x and the graph passes through 0, 2. Function f of x whose first derivative is sine x and the graph passes through 0, 2. Use corollary 2. So do we know any function whose first derivative equals sine x? Negative cosine. You remember it goes sine, cosine, cosine, negative sine. So we know that f prime of x equals sine x. So we can come up with a g prime of x also has to equal sine x. That comes from negative cosine x plus some constant. Whatever f of x is, its first derivative is sine. The first derivative of negative cosine is sine. The c disappears. So from corollary 2, we have f of x equals g of x plus c. I'll save that. So in the g of x, forget the plus c. That's where we're going to put it. So we're trying to find the function itself. Remember, also, it goes through the point 0, 2. What are we going to use this for? This is the x value, this is the y value. Yeah, because now we're going to find the actual values. We have to find what c is now. C. We got the function, we just have to find what c is. We know the y value, which is f of x, that equals 2. Cosine of x, x was 0. Cosine of 0 is 1. Add 1 to both sides. So this value of c equals 3. Now we could define the function. So f of x equals negative cosine x plus c equals negative x cosine x plus 3. So we have to first find a similar function. Where the function equals sine x? Negative cosine x. That's what we start off with. That's g of x. So our function, according to corollary 2, has to be the same function plus some value c. And it has to go through 0.02. So we plug everything in there. Velocity and position from acceleration. So, corollary 2 tells us what? We can find a function, a similar function, as long as the derivatives have the same values. Find a function with the same first derivative. That's what we're trying to do here. In other words, if we're given a function with a derivative, we could find the function that it came from. This is kind of working backwards. Velocity is 9.8 meters per second squared. That's the same thing as our gravity. It's velocity straight down. That's gravity. So this is our derivative. We have to find another derivative that gives us 9.8. Which is 9.8 plus c, well, 9.8 t times c. Why t? Why did I put a t there? Because gravity is affected by time. Because if you drop an object, it doesn't just stay, it accelerates until it gets to terminal velocity, and then it stops. Using the corollary 2 in this, to solve this, we get what? V equals 9 plus t. When time is 0, what do we get? At t equals 0, what do we get? That's the initial velocity at time equals 0. So when it's 0, we have v of 0 equals 9.8 times 0 plus c we know the initial velocity is 0, so our constant is 0. So c equals 0. 9.8 t plus c plus 0. So our solution okay. The first derivative of velocity is acceleration. So it's any falling object has a constant acceleration, gravity. Finding backwards, now I've found the velocity function with t. Because if you took the first derivative of this, what would you get? If you took the first derivative of this function, you get v prime equals 9.8. That's what acceleration equals. It's a constant acceleration. Now we have to go from the velocity function. Now we find the position function. The same way. Now we find the position function the same way. So what do we start off with? That's the position function. Position function is determined by 9.8 t. No matter what t is, it tells us where the object is. How far did it move? Now, this is the same thing as our first derivative. So we have to figure out a function whose first derivative will equal 9.8 t. The derivative is 9.8 t. How do we get, so what does this have to be originally? So remember, what does t have to have on it? Squared. Because if f of x is t squared, then the derivative brings down the t, and we get t. So 2 times what equals 9.8? 4.9. Since we know that after the first derivative, the t has to be by itself, which means it has to have a 2 originally. It has a 1 right now. We have to add 1 to it. That's, remember, the derivative is you subtract 1 from the exponent. All right, so now we know we have to use this. This is our position function. So we know that S of t has to equal 4.9 t squared plus some value c. It's got to be equal to it. At 0, 0, what happens there? Because this is how we're going to find C. So at 0, 4.9 times 0 is 0. So the C value is 0, which tells us our position function is determined by the equation 4.9 t squared. Remember, we have to look at the initial value. Check it out. Check your answer. If the position function is 4.9 t squared, and we take the first derivative of it, the first derivative is the velocity function. Bring down the 2, we get 9.8 t. Take the next derivative, so it's the first derivative of v, equals the acceleration, which is 9.8. It has a constant acceleration. So it works. The funny thing is, this is one way of finding. We start off with a derivative, we work backwards. In chapter 5, we're going to learn a whole new process called integration, antiderivatives. We're going to work backwards. I'm going to give you a derivative, and you're going to work backwards and tell me where it came from. Not just something like this, because physics problems are pretty easy. It is straightforward where it came from. But we're going to do with logs, natural logs, e functions, with everything, and trig functions, which work backwards. For example, if the derivative of a function was cosine x, where did that come from? Sine x. You test it. First derivative of sine is cosine. We're also going to do this for trig, the tangent, secant, cosecant functions. But that comes in chapter 5. That's it for this section. End of 4.2. So next time we're going to do 4.6, 4.7. Related rate problems and I forgot, it's the last section. So again, it's all going to be word problems from here on out.